All right, let's get right into this explainer. If you've spent any time in a chemistry lab, you've probably felt that sudden sinking feeling when your meticulously calculated math just completely refuses to match your experimental results. Today, we're uncovering the mystery of exactly why our chemistry math sometimes yields inaccurate results in the lab, and how an absolutely ingenious discovery from 1886 fixes the whole shebang. We're going to explore the world of abnormal molar masses and the famous Van 't Hoff factor. So here's our roadmap for today's explainer: the molar mass mystery, enter the Van 't Hoff factor, dissociation and association, and finally, testing your knowledge. Let's head it. Section 1. The molar mass mystery, or when math absolutely fails us in the lab. So, why exactly do our molar mass calculations sometimes just fail? I mean, colligative properties are supposed to be our golden ticket to calculating these masses perfectly, right? We have these beautiful, reliable formulas for things like boiling point elevation and osmotic pressure, and they rely entirely on the number of solute particles. So why on earth, when we run the numbers based on those properties, do the results sometimes look completely wildly wrong? Well, looking at the source material, there's a hard truth about those perfect calculations. You only get those perfectly accurate theoretical values if you meet two really strict conditions. First, your solution has to be highly dilute. And second, and this is the absolute crux of our explainer today, the solute cannot dissociate or associate when it dissolves. It has to stay exactly as it is. But let's be real, chemistry is rarely that cooperative, is it? Right, so when those ideal conditions aren't met, we get what's formally known as an abnormal molar mass. Since colligative properties depend entirely on the actual number of particles swimming around in the solution, any solute that breaks apart into multiple ions or, clumps together into larger molecules is going to totally mess up that total particle count. That change heavily influences the experimental colligative properties, which throws our expected molar mass completely out of whack. Moving on to Section 2, enter the Van 't Hoff factor, the 1886 solution. Okay, to express the true extent of a solute's rebellious behavior, whether that's association or dissociation, Jacobus Henricus van Hoff introduced a brilliant mathematical correction tool back in 1886. We call it the Van 't Hoff factor, usually represented by that lowercase italic letter I. It's actually pretty elegant. It's simply the ratio of the observed, or experimental colligative property, divided by the normal, theoretical value. You can also calculate it by dividing the theoretical molar mass by the observed molar mass. Basically, it acts as a reality check multiplier. It tells us exactly how much our particle count deviated from what we originally expected. And here is how we actually use that factor in the real world. The good news? We don't have to throw out our old chemistry equations. We just give them a little upgrade. We slap that Van 't Hoff factor I right into all four major colligative property equations. Whether you're figuring out the relative lowering of vapor pressure, the elevation of boiling point, the depression of freezing point, or osmotic pressure, you literally just multiply the standard formula by I. Boom. Now we've accounted for the true, real-world number of particles in your solution. Section 3, dissociation and association, or molecules breaking up and teaming up. Let's look at these two distinct behaviors side by side. First up, the degree of dissociation. This refers to the fraction of the total substance that splits apart into separate ions. Think of dissociation like a couple arriving at a crowded party, right? They immediately split up to go talk to different groups of people. One unit arrives, but it acts as multiple separate entities, or Z ions, once inside. On the flip side, we have the degree of association, which is the fraction of total molecules that combine together to form larger associated molecules. Think of this like a group of single friends meeting up at a diner so they can all leave together in a single carpool. Multiple units and molecules enter, but they act as just one moving unit in the solvent. Now, what's really fascinating is how we mathematically pin down that behavior using alpha, which stands for the degree of dissociation or association. For dissociation, the math is relatively straightforward. Alpha equals I minus 1 divided by Z minus 1, where Z is the number of ions formed. But for association, look at how the formula flips to account for n molecules combining into 1. It becomes alpha equals I minus 1 divided by 1 over n minus 1. I know, it looks a little intimidating at first glance, but it's really just a precise way to calculate exactly what fraction of your solute is rebelling against your theoretical assumptions. All right, moving to our final section. Section 4, testing your knowledge. Let's apply what we've learned. Let's kick things off with question 2 from the text, which tests our basic definitions. It asks, Which of the following is not a colligative property? Is it A, osmotic pressure, B, lowering of vapor pressure, C, depression in freezing point, or D, molar elevation constant? Take a second and think about those modified equations we just looked at.
Okay, if you guessed D, you hit the nail on the head. The answer is the molar elevation constant. Why? Well, because the molar elevation constant, often written as Kb, is exactly that, a constant. It's a specific value we use inside the equation for calculating a colligative property, specifically the boiling point elevation. But it is absolutely not a colligative property itself, because it doesn't change based on the number of solute particles.
Let's try another one. Here is question 3 from the text. The molar elevation constant is the ratio of the elevation in boiling point to what? Is it A, molarity, B, molality, C, mole fraction of solute, or D, mole fraction of solvent? This is a great test of whether you can really visualize the components of those equations we upgraded earlier.
And the correct answer here is B, molality. As the name molal implies, the molar elevation constant directly relates the boiling point elevation to the molality of the solution. We saw this earlier in our modified equation, remember? Where the change in boiling point, delta TB, equals our trusty Van 't Hoff factor I times the constant K, B, times M for molality.
To wrap up today's explainer, I want to leave you with a final thought. The Van 't Hoff factor proves that nature doesn't always play by our simple, idealized, theoretical rules. Molecules interact. They break apart, they stick together, they do their own thing. So as chemistry continues to evolve, what other foundational mathematical assumptions are just waiting in the lab to be corrected by the next generation's Van 't Hoff? Think about it. Keep questioning your results, keep looking for the why behind the discrepancies, and I will catch you in the next explainer.